Share screen. Where is the screen?
Eustace.
Hey.
Yeah, maybe you can still give people like 5 minutes to readjust and join in because yeah.
So screen. Unaniona Chiluchilu?
Yes, I can see and hear you. So and see also your presentation. Maybe you can put it in a presentation mode. Yeah, that one is okay. So I think you'll have to maybe start
Watu wako
from the
wangapi?
beginning. No, people are still joining in, but I'm saying you can maybe, yes,
Engineer Churchill,
yes.
you know, we had around 75 people and you only have 27. Let's
Yeah,
try
yeah.
to
So I'm
get them back.
telling Eustace might have to maybe start from the beginning of this presentation, maybe, and to catch, like, to try and follow what he had
Exactly.
started.
Yes.
Yeah.
How far are we?
We are still getting people to join. I hope that I see the number is going up. Let me tell the number to join because I can see it's on iPad, not in the meeting.
Sini na share ziko auzioni? Ziko? Oh.
So maybe Engineer Churchill, if we reach the threshold of 50, we can start. But we have around 39 people have rejoined, which is good.
Halo, ilikatika lakini tumeweka, ukiangalia kwa nini ya EPA utapata link yeah.
Eustace.
Yes.
I think maybe for the sake of time also and seeing the numbers is increasing. I don't know how far you had gone in your presentation, but a quick summary of what you had talked about, maybe to at least make people who had joined later to follow the presentation. Maybe you can start for the time being.
I can continue. Sikuwa nimeenda mbali.
Yeah, you can start from the beginning, like a quick summary of what you had mentioned.
Yeah. Good afternoon, good evening, everyone. We had just started, but sorry for that. The fiber cables were carried away by floods. I hope now you can hear me. So we are talking about cooling systems, but concentrate more on chillers. So cooling systems, we had talked about types of cooling, natural, forced, and free cooling, where we say the free cooling is not just free, but use fans to get air from the environment, take it to a room without passing it through a refrigeration cycle. And the parts of the cooling systems, fans, ducts, pumps, refrigeration cycle, and controls. Space cooling, process cooling, or product cooling, where you cool milk, you cool oils, or you cool any other kind of product, either meat in your fridge. Then we have what we call machine parts cooling, where we said you cool parts of the machines because of the precisions they require. You don't expect them to expand, especially those manufacturing like pipes. You're also manufacturing things like cans, cigarettes, and so on, where you require a certain size of a product. So you need to cool machines first to avoid expansion of the parts. Then we talked about, you concentrate more on water chillers because they encompass many parts so that you can see how to audit them. And a water chiller consists, that is where we had reached, where a water chiller consists of the chiller part, the refrigeration cycle part, where you have the compressor, evaporator, condenser, and the expansion valves. And the space being cooled, this is where we have air handling units, which we cool air and take it to the place. It can be a data center, it can be a hall, it can be a classroom, or it can be a place where a manufacturing room where you need constant temperatures to do a certain product. Like for example, toothpastes. You need to maintain a temperature of around 19 to 21 degrees to avoid them from melting. Then there are other things like you might be conditioning a place where you are repairing electronic equipment, or a data center, or a place where you are doing measurements, what you call metrology labs, where you have to maintain constant temperature to avoid the measuring gauges from expanding. Then also we have the condenser part, which is cooled. It can be air cooled or water cooled, like this is a water cooled system where you have a cooling tower. In another engagement, when we have time, we are going to talk more about cooling towers. Yes, water chillers are used for, we have talked about whatever they are used for, cooling spaces and machine. We have a major parts of the components of a water chiller. We have the refrigeration cycle. That is where we have the refrigerants and that's where the cooling takes place. That's the main part of our chiller. We are going to see it in the next slide. We also have the pumping system, water pumping system, because the chilled water needs to be pumped to the air handling units and the spaces to be cooled, the machines to be cooled. Then also we need, we have water pumping systems also for cooling the is water cooled. The other which are water cooled. And also we have the air handling units, which where you cool the air with the water. Those are the major parts. As we have seen, the refrigeration cycle. I won't talk much about the refrigeration cycle, but I'm going to talk it slowly. We normally have the compressor. You have the refrigerant moving in a closed system. You have to compress the refrigerant, then you take it through the condenser where you release the heat to the environment, and you pass it through the condenser. The refrigerant, you take it through the expansion valve. Then it expands and it releases it. Then you condense the refrigerant. It becomes a liquid. Then you take it to the evaporator, which is used now to absorb heat from the cooling space. Like in a water chiller, you have a jacket where you pass water through, then the water is cooled, and the refrigerant goes back to the compressor, and the cycle continues. In a TS diagram, you can see it in a TS diagram. The lower part, which is normally called the low pressure, low temperature part, where you absorb heat from a cooled space. Like if it's in your refrigerator, that's where you put your drinks or food to be cooled. Then the refrigerant goes to the compressor, you add work. It is here in the compressor where you have you add energy to the compress to the refrigerator or the refrigeration cycle. This is where we want to minimize this heat as the work or the power going to the refrigeration cycle as much as possible. And that one is enabled by ensuring that the heat transfer services, you are able to absorb as much as heat as possible. So you have to make sure that the heat transfer services of the evaporators are as good as possible. And you want to release heat to the atmosphere or to the heat sink. It can be water, air, as easily as possible. So the efficiency of the heat transfers between the condenser, fire tubes, and the environment, or the heat sink, which can be water or air, is as good as possible to minimize the amount of energy you need to put to the compressor. Because the reason why we compress air, we want to increase the pressure so that we can be able to release heat to a higher temperature as compared to the area being cooled. Because we are trying to transfer heat from a cold place to a hot place. So you need to do some work. It's like pumping. Assume like the heat is water. You want to pump water from low altitude to high altitude. So you need to do some work. I don't know whether there is any question up to that point. Good. So the pumping system, which is also part of the chiller, where we have the pumps and the pipe work. And also we have the pumping system, which pumps water to the condenser cooling parts. So you pump water to the machine parts, to the air handling units, and other parts. So in a pump, you know exactly what you have in a pump. In some pumps, your pumping systems, you have the pump, you have the piping, you have the pressure vessels, you have the control valves and the meters to measure the rate of flow of the fluid. And mainly in a chiller, you find the chilled water moves like in almost across the system. So there's little interaction between the water and the environment. Also, the same case if you are using water to cool the condenser. It's almost a closed system except in the cooling tower where you evaporate water so that you can have evaporative cooling. Mainly the systems looks more like this. The pumping system, you have the pumps, you pump through the chiller, then you pump water to the air handling units, coils, so that the air now can be, there's heat exchange between the air and the water in heat exchangers to cool the parts. Same as this is where we have like the air handling unit, and this is where you have the cooling load. You pass water through the handling unit using the pumps. Yes?
I don't have a question, but just a comment on that, because when we are auditing, especially for people who are learning how to audit such systems, one of the best things to do when you go to the facility is to ask yourself where these things are. So you cannot go to, you are told this is a chiller, then you go to log. You need to ask yourself now, where is the pump, where's the air handling unit, where's the cooling tower, and all these things. And actually, in one of the basic things that I see when the senior engineers who are auditors do, you even how to make a sketch, because engineers understand things using sketches very easily. So it's easy when you go to the facility and you want to audit this facility, you need really to know where these things are in the first place before you even start talking about it. Because if you don't know where they are, you can't give a recommendation to improve the efficiency, and you don't know what they do, why they are in the first place, what are they doing, and even in terms of their consumption. So that's what we mean by looking at it wholesomely. Someone has to really sketch and understand it starts from point A, point B, point C, point D. That way it becomes very easy to understand it, especially for the beginner. Thank you.
Yeah, thanks, Dr. Musonye, for that, because that was the aim. That's the reason why I'm doing all this for the beginner, so that they can understand the chiller on its own. It's not enough. You need to know what it is doing, where it is supplying. You need to get to the source of its load. So thanks for that. And you are going to see that in the next slides. These are just the pictures of the pumping systems. You find them well insulated with Armoflex insulators. You can see the pumps. They might be supplying different air handling units depending on what is operating at the given times. Another pumping systems where we have the pressure vessels. And mainly these pressure vessels are used in an area where probably you don't want to run the pump throughout, especially when the load is varying. You can use pressure vessels to ensure that when you don't require pumping, the pressure vessel can be left supplying water throughout the system, especially when the load goes down or not. And it's also used to control the pressure within the pumping system. So we can have one without even pressure vessels. And then we have like this one. You have pressure vessels. The vessels you see in the yellow, they are to assist in controlling and to ensure that the pump does not run throughout. All these are the pumping system in a chiller system. Then we have the other part is the air handling unit, where you have the heat exchange between the chilled water and the air. So in the air handling unit, you have the fans, and automatically the fan, there is the fan part and the motor which drives the fans. We have the ducting, which now supplies air to the space being cooled. And we have in it, you have the cooling coils, which are heat exchangers, or the heating coils. In some cases, you require to heat. So you find in the air handling units, you require to do some heating. For example, in an area where you want air at a given humidity levels, you have to remove the water. And that means you have to do excess cooling so that you can reach the dew point temperature. And once the moisture has been removed, probably you find that that air is already below the temperatures which is required for the room, and sometimes it might be very cold, like in areas where you are manufacturing pharmaceuticals, powders, and also in operation theaters. We don't want the doctors to feel very cold, but at the same time, we don't want very high moisture levels in those places. So you first remove the air through cooling, you remove the water, the moisture, but that air is very cold. So you can do some reheating, something like that, so that you attain the comfortable temperatures. So all these can be found in our air handling units. And they look like this. We have something I've forgotten in the air handling units. Also, we have the filters to remove the particles, especially in operation theaters or in areas where you have electronic systems or manufacturing powders. You don't want those powders to be contaminated. So you have to make sure that the air which goes to the room is only air without dust particles, because this air you are getting it from outside. You need filters. We have a fan. We have like reheat coils. We have cooling coils, and so on. And typically, the systems looks like this. Those just where you have the room being like this, an operation theater. We have air coming in, and we have the other air going out. One thing you should understand, like for last to save energy, sometimes the air which gets out, sometimes it can be below the temperature of the air from the atmosphere, from the environment. So you need to recirculate that air. In some cases, you can see like there's a recirculation. But in some areas, they are very critical, like operation theaters, you don't recirculate that air. So whenever you go to design a system like that for operation theaters, please don't recirculate the air, or sometimes in the washroom, don't circulate. Once the air has gone in, you throw it away, because you can contaminate the person, you can cause the diseases. But in areas like data centers and areas where you don't care so much about germs, the only thing which matters is the dust. You can recirculate the air, especially if it's below the temperatures of the air coming out is below the temperatures of the environment, instead of getting all the air from outside. This one will reduce the cooling load, the load in the chillers and water systems. There's a picture of an air handling unit. If you go to the factories and industries and many areas, you find them, they look like these. These are the ducts for waters, well insulated. The condenser is the part of the refrigeration cycle which releases heat to the environment or to the cooling sink. For those who remember the thermodynamics, you normally have the heat sinks. Those are, is the level allowed? You can tell us what is a sink. In this case, I'm not talking of a sink you use for washing hands. In thermodynamics, a sink, which can it's a place where you can add as much heat as possible without affecting the temperatures of that environment considerably. We used to talk of the environment being an heat sink, but now because of global warming, it has stopped being one. So we have a heat source and a hot heat sink. So the heat from the refrigeration cycle is released to the environment using a heat sink. Now we have the types of chillers. We have some which are air-cooled and water-cooled. The air-cooled, we use air to cool the condenser. They normally look like this. And for the water-cooled, it looks like this. One of the, here you supply air, and it's normally water in this, the cooling, the condenser. It looks like this, where you supply water. And then it is released to the atmosphere. I'm going to see that better in the next. If I go back a bit to the refrigeration cycle, you can see it better. Like here we have the condenser. Here you can either have this one air cooled, like the small ones, the air cons which you find allowed in the houses. That's where you have a fan which drives the air. Those situated out in the outdoor. you find them they are water cooled, air cooled, sorry. So it looks like this in the diagram, but when you go them in the factory, you find them the water cooled. They look like this. We talked about cooling towers to cool the condenser. These are just the photographs of the cooling towers. You can have multiple of them. You can have one of them. Inside the cooling tower, what mainly you have is the fan, and you supply water through the jets. And you have these roofers, which increase the surface area of water so that they can be able to vaporize, and you lose heat by vaporization, by latent cooling. It's called latent cooling. Mainly the connection of a water chiller to a cooling system. This can be the process equipment, can be the condenser. You can use even water cooling towers to cool water in, like in plastic manufacturing. You find them so much. This is the place you use the cooling towers. You circulate water around, it evaporates, lose it to the atmosphere, then you take back the remaining water, which is a bit cold. But you need to add some makeup water to avoid it, to avoid the concentration of particles, and at the same time to make sure that it does not drain. The evaporative cooling, that's the principle of the cooling tower. And then the whole water chilling systems looks like this on nutshell. There we have the condense, the refrigeration cycle systems. In the evaporator, we have this where we chill the water, we pump the water outside to an air handling unit. Then the water goes back. It moves in a closed cycle. The same case with the condenser cooling, where you cool from the cooling tower, you put water to the evaporate to the condenser, it circulates, pumped around, and it's a closed cycle. But mainly in the cooling towers, you have a reservoir tank somewhere to do the makeup water. So it's a semi-closed loop. These are more elaborate one. The area surrounded by the oval ellipse. This is the air handling unit, and this is the condenser. This is the cooling towers. For those who are unable to see it well in here, you can see it grammatically here. Well, you can see in the air handling unit supplying cold air back. The reason for doing this now is the whole process, all these cooling towers, these pumps, these chillers, the refrigeration cycle, the compressors, they are doing one business: to make sure that this place is cooled. So the cooling load, the origin of the cooling load is in the rooms. Because once you supply like air to the rooms, to the area to be cooled, it goes back. You can take it back if it is less than the, and in this case, I'm talking about the, where you recirculate the air, for example, like in a data center or sometimes in rooms. You get probably air which has been circulated is below there, that one from the outdoor. So you can recirculate it as an energy efficiency measure to ensure that you don't overwork the chiller. But as I said, in operation theaters, you don't, this part is not there. You close this one completely, and once the air goes in, it goes out. But in areas like data centers, like halls, you can recirculate the air. In some cases, if you find that the outdoor air is even relatively below the temperatures, the conditions of the outdoors are probably below the room which is being cooled, you can switch off the chiller and probably run the pump alone. Or there is a way you can connect the cooling tower to the evaporator cycle and supply water without running the compressors of the chillers, because they are the main energy consumers. Or you can even switch off the chiller if the air outside. For example, in a data center, you require like 20 degrees. But at night and in cold weather, you find that outside the air is at 14 degrees. You can supply it directly and have it to cool the place and exhaust the air outside. You just use the fans. That is an example of what we call free cooling, where you switch off the compressor and use the external air environment air to cool the room. Because if you want to achieve 20 degrees and what you're having from outside is 14, 15, up to say 17 degrees, 18 degrees, you don't require the compressor, the refrigeration cycle of the chiller. You're going to see that one as energy efficiency measure. But now, in energy auditing, what you need to establish is first you need to establish the cooling load. How much cooling do you want? So in your measurements, you have to do measurements to establish the outdoor temperature conditions. You have to establish whether the internal conditions are well maintained, and you measure the air, the conditions of the air released. That's the temperature of the air being released from the room. Once you establish that, you establish the cooling load of the room and see whether it is matching the design of the water chiller, so that you can know whether it's either being underutilized or it's being overutilized sometimes. But if it's being overutilized, it won't achieve the conditions. And especially since a cooling system and air conditioning systems is designed to work at the optimum point, at the extreme point. But sometimes you have temperatures from outside going low. And you find in some cases, the chiller is running even when the conditions outside are favorable to use the outdoor air. So you need to establish that one exactly from here so that you can know how you control your chiller to reduce the amount of energy it is consuming at any particular time. The same case, since or you can decide to use the cooling tower direct without running the chiller to save energy. We are going to see that one through an example. So what do you do when doing the audit of a water chiller system? First thing, although this one could have come last, do not audit the chiller unit in isolation, but consider the whole system. Consider the fans, consider the room which is being cooled, consider the air handling units, consider the cooling towers and the pumps. Because in most cases, and we have found this in the audits we get, you find when somebody is going to audit a chiller system or an air conditioning system, they learn very fast to establish the coefficient of performance or the energy efficiency ratio of that system. Let me tell you, you cannot establish that, because if you want to establish it as it is written in the nameplate of that system, it's not possible, because when whatever is written in the nameplate, the energy efficiency ratio of the COP was being established, it was established on controlled conditions. Or what you need to establish in this case is whether the chiller is running the whole system efficiently, not to establish the EER. Even during the energy audits, you don't waste your time trying to establish the EER of the chiller system at this particular point. Because even when it was being established, you don't even consider things like the cooling of the condenser and so on, because it's in a well-controlled system. So most people can measure the power input, try to measure the temperatures of the refrigerants from the evaporator to the condenser and so on. That one won't give you much and you cannot be able to achieve. And the other thing is we have found that in most of the cooling system and the air conditioning systems, people are having challenges because of challenges getting the energy efficiency measures. And the reason is because they don't measure all the parameters which are required for the running of the whole system. So in that case, don't consider the system in isolation. Consider it, the whole of it, and even the environment at which it is operating. So what do you measure? First, you measure the power inputs of all the motors. Please, if you have a pen and paper now, you can note this one. To measure the power input. And when you are measuring the power input, please don't measure the instantaneous. Measure within the whole operation cycle. Like if it's a data center, there are two operation cycles. One is the day one. You measure the whole 24 hours. But sometimes during the weekends, things change. So make sure that you capture like 2 weekends. So the ideal time of measuring, auditing a cooling system like in a data center, it's 24 hours, 7 days a week. So you start from Monday and you finish the other Monday. The reason is, as Michael Joseph said one time, Kenyans have peculiar calling habits. So you find sometimes of the day, the data centers are very idle and they become very active during the evening when people are calling each other. So you need to get even those peculiar habits when you're auditing a given facility. If it's a a disco hall, you need to see how the disco behaves during the day and during the night. And most of the time, the operation cycle now, it is either between, when do you start people going to the discos, one? Those went, is it from 9 to around 4 in the evening, 4 in the morning? So you need to make sure that you capture that time very well. That's so you have to measure the power inputs within the operation cycle. So in this case, you require very good power analyzer. Then you have to measure the ambient temperature, and not just instantaneous. Measure the ambient temperatures for that whole week on hourly basis. So you require a temperature logger which can record the temperatures for the week. Sometimes the ambient temperatures, you can be assisted by the meteorological department or NASA. NASA can give you temperatures of even your home and the humidity levels. Then you have to measure the conditions, the controlled conditions. You have to see whether they are varying, whether the temperatures inside there are varying for various reasons. Although the controlled conditions are required to be constant, because if it's a data center, for example, you don't expect it to operate at high humidities. The humidity should not go above 55%, and probably the temperatures around 20, 21. Because of those electronic equipment operate, that's the best operating points, say like 21 degrees, 20 degrees, and relative humidity of 50%. The exhaust conditions, like in this case, you need to measure the relief air and see how those temperatures or how those conditions compare with the ambient conditions and the controlled conditions. So that one will give you an indication of how the cooling load at that particular instant. Then also you need to measure the airflow rate. The airflow rates from the air handling units. You need to measure the water flow rate, the inlet and outside temperatures. In this case, you can see water is going in and out. You need to measure temperatures of water when it is going to the HVAC system and out. At the same time, you also need to measure to log the power of each and every pump and the fans. Then the condenser unit, you need to measure airflow if you are using air-cooled, or water flow rate if you are using the water, also inlet and outside temperature. The other most important thing, you also need to establish the baseline for energy consumption and the driving parameters. The driving parameters is what drives the energy consumption in that particular area in that particular space. Like in a data center, what drives energy consumption? That's the activities going into the servers, which cause temperatures to rise. And that one can be reflected by also the energy consumption of the, you can, if you are not able to get the, like in a data center, if you are not able to get clearly the operations or the data being transmitted, you can measure the temperatures, the power being consumed by the server. They can give you, there's a correlation. They can give you the relationship between the cooling load or the activities going there. So you can understand the activities going to the servers, the information being transmitted, the megabytes or kilobytes or the data being stored by measuring the energy consumption. So you can be able, because in some areas, in some places, some people will not try to give you or do the data traffic. And sometimes they don't even have it anyway. But they'll try to tell you it is confidential, because what's wrong in telling me that you are transmitting 50 gigahertz per second at this particular time or 50 megabytes? I'm not interested in the type of data, but I'm interested in the data carrier at that particular time. But you can use the power consumption to understand that, to correlate that. So as I was saying, you need to establish the baseline. For example, you need to establish what happened like for the last 12 months before you do the energy audit in that particular place. Like you can see now the temperature, the way they are varying in this case, is in from January to December in 2023 in a given area. By the way, these are real figures. I measured somewhere. For confidentiality, I won't tell you exactly where, but it's within the Nairobi region in a given data center. So this is the way the energy consumption was varying month to month, and this is the way the temperatures, the ambient temperatures were varying. So we can either ask, for example, during the month of June, why the temperatures were going down, where the temperatures were going down and the energy consumption went up. So those are some of the questions you should be asking yourselves. You can try to investigate this area. Probably the control systems failed, or there was a lot of data traffic compared to other days, or people are not operating very well. Sometimes you find even there was maintenance in the area where people are coming in and out, coming in and out. So you need to establish why, so that you can be able to know how to operate your control systems at that particular time. As I was saying, you can use data from Google Maps or NASA. These are typical Nairobi temperatures for the month of July, which was used to establish this one as well. Cooling loans, energy audit, Michilas. So where do you get the cooling load from? So you have talked all these. There's the heat generated in IT equipment in a data center, perspiration of people in conference hall, in disco halls. So by the way, you can try to compare a conference hall and a disco hall, and you see where the cooling load is high. I expect it more to be on the disco hall, because people are jumping up and down here. They are very energetic. They are releasing a lot of sweat, which requires latent heat of cooling. Can also have a heat in the manufacturing machines, in where you are manufacturing a product which required controlled conditions. Then also you need to know the environmental conditions. If the temperatures and the humidities like keep on changing, like you find in a typical air conditioning systems, the energy consumption between 2 and 4 p.m. during the day in the afternoon, you expect the power consumption to be very high, because that's the time when the temperatures are very high. Opposite at night, it's very cold at around 3 in the evening, in the morning, sorry. Any question up to that point? Because I want to take a break and brief. Wewe na dereva yuko Phoenix, ulimpata?
The driver has been saying he cannot join. I don't know, but probably his laptop has a problem, but he's blaming the link. Although on this, I would say, of course, the other thing is when you talk about taking the measurements for the variables you're supposed to use, then there is also the concept of the equipment you're supposed to use. In terms
Daktari,
of
I am able to join. I'm able to join.
Okay.
I am in. Thank you.
Hebu ongea kidogo.
I am Isaac. I have logged in. I had logged in twice. I am in. Thank you.
I'm saying you say something. Do you have a question?
No, I don't have a question. I've been listening very keenly.
So Eustace, before the driver takes us for a lecture, which I am glad it is not ready for now, I'm talking about in terms of the measurements. Then, of course, there are those measurements that I've seen a number of auditors using. I've seen, I don't want to mention names, you might think I'm marketing people, but I've seen people like Orico. I don't know if Orico is here today, Lawrence. He takes those measurements with the, you can take measurements of a flow rate, flow rate of air, water, and everything. Because some people, when you ask them to take measurements, they tell you it's not indicated on the pipe or on the system, but it's not necessarily it should be indicated there. If it's not there, you are supposed to measure, because even what's indicated, as Eustace said, is not necessarily what is happening at that time. So we need also to invest into equipment so that we can be in a position to understand or to get all these variables before we do our computation. So in these serious systems and these auditors who work, who've done audits in places like EABL and bottlers, you do an audit today, and then after next week, people want to start doing implementation. If you did the wrong measurements, you'll be in trouble because they want to implement. That's why I always insist we need to really get to primary. And we're saying you use primary knowledge, there's the basic knowledge, then you use it to build upon so that it can give you practical, it can give you realistic savings, and you can go defend those savings. If someone asks you one day to go and make a defense. So that's what I wanted to say. I have seen Eustace going back to his seat. I think you can continue from there.
Okay. Before Eustace continues,
for reminding
Eustace.
that.
Eustace?
Yes.
Yeah. Before you continue, there's something you mentioned that I think I can still emphasize on the whole system auditing. And this one can be borrowed to other systems, not only the water chillers. And in this case now, the starting point, as you had clearly put, is like establishing first the cooling loads. So in this case, even in another system, whichever system that you'll be auditing, establishing the load requirement, you'll understand whether the system is oversized, is it undersized, and then now from there, now you can focus on the part like now you're talking about the optimal requirements, optimal temperature requirements, and is the system working close to the optimal? Is it like, for example, if some chillers are set to work from a range of -2 degrees to 6, is it working close to 6 or close to -2? So those are some of the things that comes from the whole system auditing and can be borrowed also to.
Okay, thanks, Chirichil. I think we are losing you because of the internet problem. But other people, can you hear me? Good. So as Engineer Chirichil said, you need to identify the road. For those people who have been able to read the book called The Art of War, before you start fighting, identify your enemy. You might be fighting the wrong enemy, and then you end up losing everything. So as we continue on, we are talking about the parts on the measurements to be measured, and we are saying you need to get measurements in the chiller, compressors, motors, circulation pumps, and so on. These are parts of the chillers you need to take the measurements on. And also you need to establish credible secondary data. In chillers, it's good to establish the secondary data, especially from the meteorological department or the environmental department. This one assists you in setting the baseline. And also you can compare it with your measurements. And you take it like for the last 12 years, what was happening. And the power consumption, energy consumption, occupancy levels or production levels, if it's in a factory, and even if it's a data center, you can establish the consumption of the IT machines. And emphasize, measurements should be carried throughout the operation cycle for at least 1 week in a cooling system. It's good you do it for that. These are some of the sources I'm showing you of the secondary data, like this one is for Nairobi forecast. You can see how the temperatures were varying on the 28th of April 2021. The maximum we had was 24 degrees, and in that day, on those hours, the early hours in the mornings, at those times it was raining, and it continues. So on the 29th April, you can also see how it was happening. The temperatures, it was also showing precipitation, especially when it is raining. You find the humidity, like that time, the humidity was 93%. So in this case, the chiller will be forced to do a lot of removing the moisture from the water. So there will be what we call condensation, a lot of latent cooling will be required in this case. So you need to establish all that. So you might find, even despite having very low temperatures, the chiller might have been consuming a lot of energy. So you need to ask why. So that's why you need to go to check the humidity. For example, in this case, this time there was a lot of energy consumption, but the temperatures are going down. But you can see which months are these. Deliver. Are we with me? So you can see in this, there is a month of May, June, July. The temperatures are down, but you can see the energy consumption is going up. This might have been due to high humidity in the air. And that is because there was a lot of latent cooling. So you need to, the compressors were running very high. So whenever you see something funny happening, and that is why we said you need to establish the cooling load. What are the drivers of the energy consumption? In a chiller system, what are the drivers of energy consumption? It's not the temperature alone. Also, the relative humidity of the place drives the energy consumption. Because I've seen in most cases people considering the auditing air conditioning systems. They do the regression analysis vis-a-vis the what we call cooling degree days or heating degree days or degree days. They forget the humidity. Because if you learn about the degree days, they are normally used for approximation. They don't give you the real figures because they don't take into consideration the humidity of a given place.
So Eustace.
Yes.
Maybe to add, because you're talking about specifically energy consumed and the humidity and the temperature, then what comes to mind is when I'm talking about a big facility and I want to ask them to do what we always call energy management systems, then that's where submetering comes in handy. If that cooling system consumes the considerably high amount of energy for the entire facility, so that you can get the granular data for energy consumption for the entire chilling system, and then you compare with you compare with the temperature and the humidity. So someone has now to come to granular ways of doing it instead of just hoping to pick the entire energy for the whole facility. Then you want to regress against the days or against the temperature or against relative humidity.
Yeah, yes, specifically that's the whole idea of establishing the drivers of energy consumption. You need to put your school, what you learned from the school, you combine it to what you learned from the Juakali and what you get from any other kind of knowledge. Don't neglect any knowledge. We used to have a program called Feed the Nation by Leonard Mwashegwa. For those who are existing in the 1980s, it used to be called Feed the Nation. And they used to say scientific methods and traditional methods, all of them contributed to food production. So even sometimes your Juakali knowledge can be useful, and you can even transform that Juakali knowledge to be formal education. So specifically, when you do a measurement, like in this case, you can find this an example now of what you are supposed to measure. You measure the time. I don't know whether you are going to get Einstein to tell you whether time is relative or absolute or whatever. So whatever method you use to measure time, we need to know at what time these things happen. Year zero, I'm assuming zero is, in my case, is in the midnight. So at that point, you check the set conditions in the room. This one tells you the control systems was very good. It is set at 19 degrees. The reason of getting the set sits in the set point condition to see whether it has deviated. Probably it requires 19, and sometimes you find it is 18 or 17. That one means it's a red flag because you'll be overworking your system, the cooling system. Then you set the set humidity 50. That one was okay. Then the enthalpy of the conditioned. Please, this is a calculated figure. I don't think whether there's any measure instrument for measuring enthalpy. And in this case, you can get it from your psychometric charts. And in these days, you have online psychometric charts. You only need to give them the temperatures and the humidity. And they gives you all the figures. The relative humidity, they'll give the relative humidity. They'll give you the humidity ratio. They'll give you the dew point temperatures. They'll give you the wet bulb temperatures. They give you the density of air even at that particular time. All those parameters they are going to give you. And the ambient temperature, this is what you get. This is the relative. These are the ambient temperatures. Then you measure the relative humidity. I know the numbers are a bit small, but you don't worry about the numbers. But if you can be able to see the top, those are what you measure, the parameters you measure. The rest is what I mentioned, which might not be correct, or you might not very accurate. Hello, can you mute, please? And stop.
Osia, help us to mute people.
Please stop fighting.
It is muted.
Oh, thanks very much. What the driver was talking. So I'm saying that the parameters to measure, those are the parameters you need to measure. And these are enthalpy, these are calculated value, which will be very important. And in this case, especially when you are dealing with the ambient temperature, you can see calculating the energy required to convert that air, to change that air from say 18 degrees, 84% relative humidity to 1950, you need to remove some water. So there is both the sensible cooling and the latent cooling. So in this case, you want to use the temperature, the change in temperatures direct. That is why you need to. Do you want a break? Yeah, let me show you this, then I give you 5 minutes break. You breathe, then you can ask a question. As I said, when you are measuring when you're calculating the heat required to be removed between the ambient conditions and the controlled conditions, use the enthalpies, not the changes in temperatures, because there is both latent heating, there's both latent and sensible cooling or heating. The other thing you have to measure is the exhaust temperatures of what is getting from the room. Then you need to measure the airflow. You need to measure the water flow. You need to measure the temperature of water going to the HVAC AHU unit. You need to get the water temperature going inside and outside. Then you measure the power consumption of the compressors or of the oil chiller system. I'm going to give you 5 minutes break. But as you have the break, you can ask.
Maybe you could just finish.
There's an example. You can ask a question.
I was just wondering, maybe you could just finish the presentation, then now we could get to the question time as we break.
I was asking, probably there's something which is not clear. No problem. So we are on consensus, we continue. You see me, I have an advantage of having a break is just to call Chiri to talk.
Oh yeah, that's why I was thinking that you need to break yourself.
Huh? Oh, I take break myself. I have no problem.
Yeah, that's what I do.
No, I have no problem. Yeah. I can talk for 6 hours.
You saw, for myself, now that I am using a phone, you know, I can take a break to the washroom and all that with the phone, so I have no issues.
Okay. Oh, that's a good break. So after you have measured and recorded that data, and when you have done an energy audit, this is the first data we would like to see. When you do our calculations, we want to see the source of this data, even your client and everybody, because we need some form of traceability. So in that case, you can calculate the calculations you can make here now. You can calculate the heat released by air to the chilled water using that formula. Everybody can see that. You can see heat absorbed by air, absorbed by water from air from at the AHU. You might be wondering, probably these things should be equal. No. The reason of calculating both is to establish the effectiveness or the efficiency of heat transfer of the AH unit. In ideal cases, they should be equal. But in the real sense, there are some heat which has been absorbed by the parts, the coils, which have been used to increase the temperatures of the coil or of the fins of the AHU unit. Also, there is probably poor heat transfer due to the dirt or poor heat transfer because of the insulation of the resistance of the cooling coils. And in that case, you are supposed to calculate the effectiveness or the heat transfer efficiency of the AH units. And in that case, you can see it's 88.1%. And probably you can try to improve it by either doing the cleanup of the cooling coils. You check whether at the time you are doing your measurements, whether they were dirty or not. You can clean them and continue and see whether it's going to improve. You need also to get the manufacturer's specification, what the heat transfer coefficient of each AHU unit. Or if you make a new design, if you design a new air conditioning unit. During commissioning, you need to establish the heat transfer coefficient of that and set it as a benchmark. Is that clear? Then the cooling, the capacity factor is, you get the capacity factor of the whole system. That's why you need to measure the temperatures of the air getting out and the air going in. Because once you calculate the cooling load, how much the air going into the room has absorbed, you can calculate. In this case, I missed to do this calculation. You might be wondering where this 7 is. I was preparing the slide. I've left it where calculating. But since I'll be sending you the slides, I will send you this calculation. So because that one is calculated between the temperatures of the air, of temperatures of the controlled service, the controlled temperature, and the exhaust temperatures. You can see the exhaust temperatures. That's where you get the airflow, this temperatures difference, and you calculate that using the same formula as for this, except now the change in enthalpy will change into the change in temperatures, because the air going out is at the same relative humidity as this if it's a data center. But now if it was a disco hall or a hall or people where they are eating where there is a population, you can establish that. So that's why you need to establish clearly the process which is going on. So like now you can see the capacity factor of this one is very low. So this one can raise a red flag, and it's going to be the question. The other one, you can get you can measure, you can calculate the total energy consumed within the 24 hours. If you have a very good data logger, it can measure you this energy directly. But if you have the one which is measuring instantaneous powers, you can calculate them using the graph. You just calculate the area of the graph using the trapezium rule or any other way you can get the total energy being consumed within 24 hours. But if you have a very good data logger which measures the total energy consumed within that period, and that's why the type of measuring instruments, they are very good. Now, from the data we have collected when you present it like this one, it might be confusing and it's not showing you anybody. It's good to trade it or to draw a graph. Like for example, now you can see the way the power consumption is varying. Vis-a-vis this, the controlled temperature is constant. Vis-a-vis the exhaust temperature, you can see the temperatures are increasing. Exhaust temperatures. Vis-a-vis also the AHU, the ambient temperatures. As the exhaust temperatures increases, the exhaust temperatures are increasing. And you can be able to trend and see how it is varying with how each parameters is varying with each other. Especially the main thing we want to reduce is the power consumption. How is it varying? At this point, you want to establish the temperatures were very low, but the power consumption is high and all these positions. And especially at this point, it is very early in the morning. What might have happened? Is it the control systems which failed? Or the other factors which contributed that? Or probably at this point is when the time people come in these data centers, and probably there is a lot of influx of air, and you want to see from the external through the door, and you want to see whether the air curtains are functioning very well, to warrant all this, or is it a bad behavior of people? So you have to establish all these abnormalities, because you don't expect the power to go on when the temperatures are very low, especially early in the morning, and especially if it was not raining. Because if it was raining, now you can conclude it is because of the latent cooling. So in this case, having gotten all that data and all those parameters and having drawn all those graphs, there's a verdict you need to draw. And here you have to answer questions. Chilichil. Engineer Chilichil.
Yes, Eustace, yes, I can hear you.
Now from here, now you have to record the people who are going to answer questions, because you are going to give marks, and those will determine whether your license as an energy auditor will be renewed. The point.
We're asking the level first.
No, I've become a journalist now.
Now you have to answer questions. Activism itaisha sasa. So from all the data we have received, because you have been following, from the measured parameters, your calculations and the graph is the HVAC system or this chiller system. Is it energy efficient? If yes, say why. If no, suggest 3 measures which can be taken to improve the efficiency. And in some cases, the reason why I'm asking, yes, in some cases I have seen people coming saying that we didn't establish any energy efficiency measure in that system. It is new, it is blah blah. But you know, if you ask them the data which they have used to conclude that, they cannot give you. So whenever you do an energy audit, it's not a must that you are going to get a measure. But if you fail to get a measure, you must prove it empirically with calculations and the data you have used. So is this system efficient? Chili, you can get the people who have logged in and call them by their names. Eh?
I have
can
seen
start.
Senegal here. Albert.
Engineer, how are you?
Fine, thank you. I saw you wanted to say something. I know you worked in data centers before when you used to be in a cooperative bank.
Yes. So I'm actually following up. This is very important.
I'm asking now from the calculations we have done, is this system efficient? Energy efficient?
Maybe Eustace, you can display the calculations again for people to. Yeah, that part, exactly, that one.
That's the data.
Yeah.
But don't worry about the data. The calculations I did, the chilled, the air released, the heat released to the chiller, chilled water is 30,485 kilowatt hours. Heat absorbed by water within 24 hours is that 524 kilowatt hours. Then we have found that the efficiency ratio is 88.31. The capacity ratio is, the capacity factor of the whole system is 22.3. The energy consumed in the facility is 10,000 by the chiller is 10,590. Then the graphs are showing these are the way they look like, and especially if you want the one which has power, which is showing a bit better is this one.
Well, I think it's automatic based on how you have asked the second question, that the first question definitely is not efficient. I mean, and so if you say it is efficient, then there would be no reason for you asking the question, the second part. So by studying your question alone shows that it was not efficient. I haven't studied the data, so that is my answer.
You have to give the reason why it's not efficient. These are the data, these are the calculations I've given. This is the efficiency factor, is the capacity factor, and these are the way the graphs are looking like.
Well, I just based my argument based on the fact that you asked a second question, which showed that if the first question was yes, then you wouldn't have asked.
Whenever I don't want to, but that's not a very good way of answering. I've said, is it efficient or not? If yes, say
maybe
why.
first,
No,
maybe
suggest
I can ask a question. you know, you have your calculated efficiency. Maybe what was the rated efficiency of the chiller on the nameplate, so that we compare the two and then maybe be able to make some conclusion.
No, as far I've asked according to the measurement parameters, your calculations and graph. Assuming the nameplate is not there.
Go back to the calculation.
I would think maybe at 88% is not that badly off, but I would have wanted to compare it with the nameplate.
No, the efficiency, this is the efficiency of the HVAC, the heat transfer of the efficiency of the HVAC. But now there is the capacity factor of the cooled space. See, there's the capacity factor.
So with this value, you're supposed to tell if it's efficient or not, by the way. That's what I used to just look at. And I remember saying, ideally, you gave us a value for AHU, what it's supposed to be, and what it is right now. I think for me, I was following a bit closely. And then you are now talking about the capacity factor. So with these two values, actually, you should be able to tell. And you told us the answer for question.
And that is why I put them in red.
Mm.
So tell me whether it is efficient or not. From Laviole, from this.
Because generally, that's why we start talking to our client from. A client will want this final value for AH unit. Then you tell them this is the value that I've found, and this is the value that we desire to find. And Eustace even gave us specific things we can do to make sure that this value increases. Actually, I remember him there saying that, probably because for me, I'm a bit of a good student. I was following him closely. I'm also learning from him. But then these are the numbers we need to look at. And the important thing is, how do you arrive at these numbers? Then number two, what is the ideal number? Then what should be done to get the ideal number?
And remember, when you are doing audit, all these measurements can be done by a technician somewhere. I'm not undermining their intellect, but, and they can also do these calculations because these formulas are everywhere. You can calculate all these, but what do they tell you? For example, if a capacity factor of a machine or a system is 22%, what does that tell you?
Well, I'm also confused, but I honestly saying that I've never gone through that calculation personally. But based on my experience with machines, 85% is normally a good measure of efficiency or mechanical efficiency. So when I find 88.31%, I tend to think that it is doing well, but doesn't mean there is no room for improvement. Personally, I don't know what is capacity factor of 22.33. I don't know whether it's supposed to be higher or lower. So if the whole class is I have a problem.
Let me put it like this. The capacitor factor of a machine is the load divided by the design of the machine. For example, this we can say like this chiller is designed to cool. Allowed load 34,524. But now you can see, as I said, this is the cooling load from the room, which is being cooled. This is the heat generated by the activities in the data center inside. You get it?
I get it that the useful load
is on site
7,700, but then we are using or generating 34,000 outside, which may not be necessary. So I mean, the capacity factor then means that if we could be anything above 50% would be better.
Yes. Logically, the capacitor factor of any system should be more than 75%. It's like a motor. This means the whole chiller system is being underloaded, and you need to establish the reason. Is it the design?
That is a load factor.
Yes, the capacity factor or the load factor.
Then that's quite low. That's quite low. You agree? Yes.
And meaning the system is inefficient.
It is underutilized, I would say. If they add more load, they would handle for maybe to get to 75%.
let's start from the first thing. If there's the load, if there's the heat I'm supposed to remove, 7,000 from the room, I don't require to run the whole chiller. Probably the chiller compressors, the control system has failed such that it's not detecting when the load is going down or up. So it's being inefficient. Because I'm running the chiller, I'm running the pumps. Why should I be running the pumps just to cool 7 loads when I have the capacity of cooling this 34,000? That's what you should be checking. Because if you look at the chiller cycle, all these systems are supposed to remove heat from this area. But you find, for example, because the cooling load is very low, I'm required to circulate a lot of air because the valve is supposed to open depending on the temperatures which are released here. If the temperatures are very low here, and that one can also be seen from the data, you find the temperatures most of the times are between 20, 23, like at night, they are 19, 20, and so on and so on. So in that case, it means I'm still running the chiller, generating a lot of cooling, which is not required. So probably I should have switched off. So make sure when you get the capacity factor or the load factor, it tells you a lot. So the system automatically is not efficient. And if you had not measured all these parameters, probably you could have said you are not getting the energy efficiency measure. The other one is somebody asked for the nameplate. Sometimes you might not get the nameplate. You are supposed to do your measurement to establish the effectiveness of the system at those conditions. So even at these conditions, the system is not. So now, which are the energy efficiency measures which you can suggest now that you have seen it's inefficient?
Go back to the diagram.
Which one?
The one that shows the air handling unit and the rest.
That one.
Yes. Now, my question then would be, as I look at what are the measures I would take, I'm looking at what is the intake of the energy used, and I can only see is like the fan and the water pumps. If the water volume is to go by, and the compressor maybe. So basically, it would be to look for a smaller fan and air compressor and reduce the amount of water circulating, probably the system size. That would be my take.
Okay, another person. That's a good attempt.
Is it an attempt or I have won? I mean,
Apple may score 30%.
That's a good one, Dereva, because when I'm teaching introduction to energy, I say energy is a function of power and time. So power or time, just playing around that. Yes.
That's a good. I'll tell you why you didn't get 80% in the level.
Yes. I will be waiting.
Somebody else?
Chomba is in the sitting. Chomba is somewhere.
Wait, chill. Where are the people? Taja mutu jina hapa.
Chomba, I haven't seen Dennis Kariuki here. He's giving comments in the, the problem with engineers, they are very shy. So he's giving comments in the chat instead of talking. Dennis,
you're saying what?
Kariuki. He's chatting in the chat room instead of saying his comments here. Yes, Dennis, you can say something. Kariuki.
Yes, I'm here.
Tell us something. You start asking questions now to improve the system.
I wanted to suggest maybe introducing a receiver in the water pump line so that to improve the heat transfer between the air and the water. So when there is low demand or the driver of energy inside the room when it's low, the water pump does not need to run at full load in circulating it.
Yeah, that's a good attempt, and it's also good. That's good. That's a good one. Now we have two. If you implement those are good. We are remaining with one because I had asked for 3. Eh? Although there are more than 5. Somebody else?
I've seen Engineer Marambe here. I've seen Engineer Nguni. Engineer Marambe, you are a mechanical engineer like myself. Probably you could add something.
Hi, Daktari. Apologies, I've
Yes.
just joined, so
Okay.
I'm trying to follow before I can contribute.
Fine.
Thank you.
You can check when you joined.
Sasa hizi mahesabu zote umeweka hapa, mtu atacheka aje? But I will try to let me follow. I've just
Okay.
joined the meeting, so I can't contribute.
Fine. That's good. Okay. I wish to see Chris here, Chris Mori, because I know Chris has done a lot of work in cooling systems, but Chris he joined the first. I think he has disappeared. I was looking for someone else to harass.
But what was the question again? What is the question,
Just
Eustace?
the chilling system, Eustace, repeat the question to Engineer Marambe.
If he has joined a bit rate, it might be challenging, but we had asked from the calculations we have made, the graphs and the parameters we have mentioned, is the HVAC or the air handling unit or the cooling system efficient? If the answer is yes, tell us why. If the answer is no, suggest 3 measures to improve. That's the question. But to save on time, the Reba has said something good. The other one was who? He has also said something
Dennis,
good.
Karaoke Dennis. Yeah.
Yeah, karaoke, introducing a pressure vessel is good because you find if the cooling load is low, you don't need to require to run the pump. You need and I said it as we were discussing the pumping system, why we introduced the pressure vessels, is to release the pump from running throughout when the runs good. The other point is you find during this time you can bypass the chiller, which consumes a lot of energy. You know the compressors are the largest energy consumers. Sindio? You can bypass the chiller and use the cooling tower. That's another good point. You can also introduce, in this case, because we see the road is varying and the temperatures are varying, you can introduce a VFD in the pumping system, especially when the outdoor air goes down. But in most cases, for safety, don't touch this fan. The fans extracting air and the fans pushing the air inside the room, don't touch them. Let them work full blast. That's a security measure. You can have VFDs on them, but it's not very, very good because you can choke the place. But you can joke around with the pumping system here, the chiller and the cooling towers, because now a data center is very critical. Eh? So you also need to understand whatever you are dealing with. If it's a theater, you don't limit the amount of air. If it's the people inside the room, you don't reduce the amount of air going inside. So I think those measures are also good. You can introduce VFDs and also you can introduce the control system to ensure that the the compressors, all of them don't run, because in this kind of a system, it might be having several compressors, which can be switched off and run one at a time. Any question? I'm almost ending. Any question?
Do you have anything, Eustace, do you have anything, will you recommend to do some waste heat recovery in a data center, let's say in East Africa?
Yeah, if you have somewhere to use that heat, you can recover it.
Yeah, that will be another measure to recover it, to use maybe in the, to recover it, to use
if I may use, you have to check where the data center is replaced, whether there are people taking showers there, and see whether you can use that hot water there. Or else it might not be very useful. Before you recover heat, you have to identify where to use it. If it was near an hotel, it can work. But the other thing is, that is why we normally talk of understand the process. If there is a swimming pool allowed, you can use. So the process, understanding the process and the area you are in is very, very key. Because you introduce a heat recovery, for example, in these data centers for Airtel, Safaricom, and they are in a very isolated place. Do you have people, do you have somewhere to use hot water there? Heat recovery is good, but you have to understand where you are using it. Yes, like if it is an disco area, it's good because you find they are accompanied by clubs. Probably they are in a hotel, a 5-star hotel. You can.
Eustace, there is a question from Inapro Africa.
Aya, karibu swali.
Yeah, thank you, Eustace. This is Albert. So I just wanted you to also comment on the power use effectiveness as a parameter that is used for benchmarking, especially data centers. And we know that there are data published by the Uptime Institute to rate data centers. So sometimes, again, we even before you monitor all the other parameters, then it's also good to understand what is the power use effectiveness of, for example, if you are handling a data center. The other aspect, again, is normally the temperature of the white space. There's a lot of tendency to overcool the servers. And I think there are recommended temperatures. I think as Engineer Phoenix had said before, like banks, they tend to play safe. And one of the things, they don't want the data center to go down due to any reason whatsoever. It's so critical to the operations, and so they will want to keep that temperature as low as possible. So sometimes trying to convince them that overcooling the servers again contributes to higher energy consumption sometimes becomes a challenge. But the power use effectiveness, especially for comparing one data center to the other in terms of energy performance, I think is key. So maybe Eustace could comment on that. Thank you.
Okay, that's something very good, but in this particular case, we were just auditing a cooling system. It's only that we ended up being in an example of a data center, but we have also, in any system, the energy utilization. I think the power utilization index or power energy effectiveness, whatever they call it in the data centers, is key. But all that is what we call the energy utilization index of any facility. You need to check it very well. That one is very good. So whenever you are auditing any facility, and that is why, like in this In this one, our utilization index is the capacity factor. That's why we had to calculate the capacity factor. So if you are auditing the real IT machines, we could have gone to calculate the effectiveness, the PUE, energy utilization index of
Actually,
those.
Eustace,
Yes.
and what Albert is saying makes sense, because sometimes, you know, when you send someone to audit a facility, even like in here in this office, we just tend to neglect what the IT equipment uses. I know it's outside the scope, but then those are the kind of things, if you really want to know what's happening in the data center, you need to look at the entire equipment, look at the IT systems, then look at the cooling system itself. Then you now have to put that all together, because sometimes we tend to ignore what the IT systems are consuming. We just rush to the cooling part. That's the thermal fluid system. Then we avoid these other ones. So maybe just as a takeaway point from our auditors, one has to look at the consumption of the equipment. There's a student I'm supervising who's doing some work on green buildings, and I actually told her, I don't know if she's in this meeting, I told her to go and make sure that she's logging by checking what the IT equipment is using, because that's one thing. You remember there was a story, I don't know if it's true, of someone who constructed a library, I think a two-story building. One floor was having a library. Then he forgot to compute the weight of the books. So that had a problem, because you compute everything and you forget that library is supposed to be holding books. The same thing when you look at the chillings, the cooling system for data centers, where we have the IT equipment. Someone has to also to factor in the IT equipment. Thank you very much.
Yeah, I think probably I was very fast during the starting, and good for like a reminder for the other people. Probably we might have gone very fast. We talked of you have to identify your cooling load. And I said for data centers, you have to establish the relationship between the energy consumed and the operations, the megabyte, the gigabytes, or the bytes which are being transferred at that particular time. I remember talking about that. If I was, and those are the use you choose to use the productive use of those machines. Probably I was a bit fast when talking about.
No, you are clear, Eustace. You are clear on that. I remember you saying some people don't like sharing their data speed.
And there is a way you can bypass them by calculating, checking the energy is consumed. I talked about that. Yeah. So you have to identify your cooling loads very well. You don't neglect any cooling load. And that is why I said from the book of The Art of War by Zhang Chu, you need to identify your enemy when you're fighting. But it's a good reminder for all of us. The other one is about overcooling or undercooling. Now, there's something we always say on energy efficiency. The comfort of the customer comes first. So if the bank have told you we want to be operating at 12 degrees, it's for you now as an auditor to ensure that one is maintained, because that is what, if they have decided that, they should not be going to zero or what. So remind me the name of the question first. So you cannot say the banks are undercooling or whatever, but they should tell you what point do you want to operate. Like in this case, we can see the set point is 19. So they should tell you their set point, but don't try to force them to go to 18 because you found another bank going at 18. So because they are ready to pay that for their own reasons. And you find that one is very funny, like with this, we call them pizza in, cream in. Their policy is all the lights should be on, whether the sun is what or what. You are visited those places. I went to one of them and asked them, why do you put lights on at 12 or whatever, and it's very hot? They said the company policy from Amblood is the lights should be on. So you need also to check all those things. You need to check at what point the client is operating. If he insists on that point, now you have to juggle around that point and see whether you can get measures to maintain that point. Don't force them to go below, because they will give reasons why they should operate on that. But if you find now it's fluctuating.
Eustace, Nereva's hand is up.
Yeah?
Nereva.
Eleva.
Yes, Lord, the hand. Maybe it was an old hand, but I've been seeing it here, so I wanted to alert you so that you can speak.
So as I was saying, like you can see these places we have set at 19. Don't come and tell them other guys are put at 21. Isaac. Eleva. Okay. So what I was saying is you have to juggle around this point. But don't try to force your way to save energy. Like this one, you have to make sure that it's set at this point. So the problem could have been if at the time it is 16, 15, and so on. That's where you get their control systems. But I think that one is a bit clear. So the auditor's comfort, the client's comfort comes first. Then you'll be able to work within that particular range. Is that clear? Good. So very quickly now, we have done most of the things now is to talk about, to see the instruments. I won't talk about them very much when you're auditing a water chiller. Many of the things you need is the temperature and the humidity loggers. You can get the ones which can log over a period. They can store data. Those are the best. You can get the infrared to counter check whatever you have logged. As we said, it's good to measure within the cycle, but you won't be able to be throughout to measure within the cycle. That's why you put the loggers. But once you come, you can counter check or you can calibrate with your infrared thermometers. You need meters, flow meters, ultrasonic to check whether the fixed meters are working well. But the fixed meters are the best. Ultrasonic meters, they're just to check, or they are used in case where you don't have meters for comparison. They are not as accurate as the turbometers. You need to get the airflow meters to get the flow of air. You need the data loggers, the power quality analyzers. You can use the portable ones, but currently the best now you can use are like the Engage, which you can even go online and which you can even measure several loans. Like this one can measure up to 15 loans. And sometimes when you go to a data center, as we have said, you can see there are several motors. It's good to advise, especially if you are doing a design, because some of us are engineers, make sure that all these are centralized in a good control board. Because sometimes you find that the water chiller is being operated from one point, the chiller is operated from one of the compressors, the fans. If you can be able to have all this in one point, and that is what is happening these days, one control board where you can be able to log all of them very easily. That one is very good. And that's why you can even use this, the Engage, and log many loans. This is just an Engage like this one. Potential areas of improving energy efficiency. We have talked most of them, but before we talk of it, you can look at this graph with also a cooling system, air conditioning system, a split system. You can see there is the power line, the power consumption over the 24 hours, and the temperatures. That's why you can see whenever you identify a queer behavior, please try to understand what was happening at that point. Did the system control systems fail? Did it start raining at that point? Or what happened? So that you can see now, instead of the temperatures increase, the power is increasing. Now you can see between 3 and around 6 in the morning, The temperatures are reducing, but the power consumption went up. So you need to identify what is happening in this area and give an explanation, because it can be recurring throughout. Probably it was poor setting of the control systems. And probably that might be have been a major source of energy consumption, because these are many hours, 3 to 6. So as you identify the potential energy savings, understand how the system, don't just present this graph in an energy audit and leave it like that. Take it and go back to the client and get the history of what happened. You might not get it, but you can log.
Eustace, there's a question here from Jeremy Omare.
Yes.
Some people fear talking. I don't know why Jeremy fears talking, but he talks a lot when I meet him. His question is, what's the impact of maintenance management of water chiller systems to the overall efficiency? Just maybe after you've done, you can talk about how maintenance can assist to improve the efficiency.
Since we are talking of energy savings measures, let me put it, for every system, every machine, even human beings, maintenance is very key. Because what maintenance does is to try and bring the machine or the system towards the design conditions. And you remember when I said, if you design a cooling system, you need to audit it that first time. You need to do what we call commissioning to ensure you set out the parameters. So maintenance management system is very good, like to identify when the transfer services are getting dirty, when the motors are deteriorating, when all the heat transfer system are deteriorating. It's very important in energy savings. One of the most things, in fact, one of the key areas of energy savings is you find a poorly maintained system. One of the low-hanging fruits is maintenance. So as I was saying, if you find a peculiar habit, like Michael Johnson, you should try to understand why. He talked of Kenyans' peculiar calling habits, but instead of understanding why Kenyans like calling at around between 6 and 1, he failed to understand that's the time boyfriends and girlfriends are confirming whether you are coming for the date or not, for supper or not. There is free cooling. Once you identify low temperatures, especially at night, you can introduce free cooling. All this we have talked during our presentations. You can also do, you can bypass, like we said in the chiller system, you can, if you find that the temperatures of the ambient conditions are relatively low, you can bypass and use the cooling tower direct instead of using the chiller to cool the system. And that one, this is a good photo of showing how you can, or a diagram of showing how you can bypass. You can get the water from the cooling towers to the pump. Instead of now taking it to the condenser, you stop the cooling, you stop the chiller, you close, you close this valve and this one and allow water to go to the chilled water network directly. If you are sure it's not going to interfere with the quality of water and the quality of chiller is the same, but of the chilled water cycle and the quality of the condenser water is the same, you can do like this. But if it's not the same, you can introduce an heat exchanger in between to ensure that there is no mixing between the water from the evaporators and the water from the condenser. So bypassing the chiller system, the refrigeration cycle, is good, and that is what we normally referred to as the free cooling. The other measure is you can try to check the set points. If you find that you don't require very low temperatures, you can, at the evaporator, you can try to make them go as possible. Probably if you require temperatures between 6 and 8, why do you go up to 2? If that was the set. If this one can do well, it's okay. Like in our case, which you are asking the measure, The other measure could have been to reset the temperatures, the evaporator temperatures, because probably you don't require to cool all that much. You can save 1 to 2% of the energy. The other point, you can also reset the condenser temperatures. You don't have to go very high in the pumping system, or you go slightly low in the whatever the temperatures at which you want to release. If the atmosphere is the environment, it's relatively at low temperatures, you don't have to compress the air so much. And I think you can find you compress it up to very low, slightly lower pressures, then you release it to the atmosphere. You can save. The other one is use a retrofit. You find if there are any compressors, after doing all the other measures, the retrofit should always come last. So you do the retrofit of the compressor, you can do the retrofit of the pumps, and so on. So you need to establish one which has a better working range. If you find probably you don't require a reciprocating compressor, which is inefficient, and use a screw compressor for those runs, you need to check the runs and do the retrofit. So in this case, probably at one point, you need somebody to give us what we call the technology update. You have to keep on updating. As an energy auditor, you have to keep on the new technologies which are coming so that you can know what to suggest during retrofit. So those are just some of the compressors. I won't talk about so much about them. Probably we can have some other times talk now on the efficiency of the equipment. This time we are talking of the efficiency of the systems. Although the efficiency of the equipment of the system is as good as the equipment, but the new now efficiency of the equipment, of the pumps, and so on. Like you have another one talking about the pumping system. So probably he also talks about the pumping system in a chiller in details, how to improve specific equipment. These are the equipment, the compressors, these are reciprocating, these are the centrifugal one. Currently, we have some centrifugal compressors which are using magnetic bearings, which have improved the efficiency by around 2 to 3%. So you can, if a retrofit is required, you can recommend that instead of using the one which was the original. And as the compressor retrofit, you can, this is where the maintenance comes in, the cleaning. Somebody who asked about maintenance. Maintenance is good. Clean the evaporators, you clean the heat transfer, you clean the heat transfer services, you check whether the chilled water is dirty and replace it. After some times, you have to check that one. The valves, the control valves, you can change from the expansion valves to electronic valves, which have a quicker response, then saving the time for cooling. The response time, because the expansion valves are a bit slow. So before you change the response time, either for the refrigeration cycle or the cooling systems. Yeah. Those are how the control, the thermostatic expansion valves operate. These days they are being replaced by the electronic ones, which will improve the efficiency of the system. Because improving the response, it's good. Most of the times the fan run on 100%. So you need to check. You can retrofit using electronically commutated fans, which are more efficient. They have the potential of 3 to 6%. Commutated fans upgrade. The controllers, you can get the controllers with better response, such that you don't maintain, if you detect environmental conditions have changed, you need to respond as quickly as possible. You can use VSDs on the cooling tower fans, the pumps, or the chillers, the AHU fans, and so on. But as I've said, you should be very careful now when dealing with the AHU. Don't try to tamper with the AHU, especially in the data center. Before you tamper with the flow of the AHU funds, check the operations going there. Can they be affected if the airflow is reduced? The VSDs, either in all those the handling units.
You start on checking. Maybe I would wish to bring maybe the team also to the attention of what you call HACCP, especially if you are auditing hotels. I know Eustace have been stressing on that, the issue of trying to stop the funds from supplying air, but there's also a protocol that most hotels adhere to. It's called hazard analysis critical control points, HACCP, and you find most hotels or these international hotels are signatories to that. They use that. So when you are even recommending those temperature set points for the hotels, especially where they are keeping food, you need to consult with them, especially with their safety person, to see if that makes sense. So because you can recommend things that most of the times they don't implement, and when you ask, they tell you about that protocol. Thank you.
Yeah, that one comes to the point where now, before you audit, understand the operations of any facility. Understand their requirements, understand their comfort, and everything. Questions?
I'm still holding on in case there are people who left the coat in the offices. Now, I was trying to imagine if there is a system, I go and audit a system, especially for those who manufacture gas cylinders, acetylene and the like. I found that the chillers they use, if you look at the load, the total load, compared with the others like the oxygen plant, and you do Pareto principle, you realize that the motors involved in the chiller system is too small, such that even if you are trying to propose the measures to save energy, is a drop in the ocean as compared to the plant consumption. So basically, would it be a problem if you thought that actually that is too small to think about? Because you may even go to, for example, I give the highest consumer like base titanium, and then you start counting lights. Would it be in order to say you saw like the chiller had the smallest consumption compared with other systems? Thank you.
Yes, I agree with that, because there is a point you cannot go below. And you have to prove that empirically, and with the statistics. That's why I said statistics are very good. Because, for example, if you tell me to get a water pump for my house, which is less than 0.75 kilowatt, and that is the smallest you can get in the market, that will be the sort of engineering, because as I have said, you should always be up to date with the technology. So it's correct. If you can prove that that is the smallest you can get in the market, and you have measured, so you should get the other areas of improving efficiency, not just retrofit. And that is why I said retrofit should always come last. Si hapo ni sawa, dereva?
Hapo ni sawa. Thank you. Thank you very much.
Then Engineer Marambe has a question.
Yes.
Or a contribution.
Thank you again, Phoenix. And this is Godfrey Marambe again from QSAM Energy Limited. Eustace, while you are doing this research to talk about these cooling systems, especially in data centers, did you come across anything related to this new technology on liquid cooling? Maybe you can try to explain to us a bit, if you did, because I've heard something about liquid cooling, but I'm not sure how it works.
Liquid cooling on what?
Liquid cooling of the racks themselves, of those racks in data centers.
Yeah, this is where now you introduce the liquid probably, which cannot affect the electronic parts in the racks instead of using air direct.
Yes. So is it more energy efficient than the traditional cooling?
I can't authoritatively talk about it, but what I can say, Probably you see in data centers, sometimes some racks are not operating, others are operating, and so on. So the liquid cooling can be used now to make sure you only cool a section or a given rack if it's the one which is generating more heat. Because you find sometimes some racks, you see in these data centers, people come and they put their servers there. And at times, probably there's a time when my servers from a certain arc are not as active as another given arc. Instead of trying to cool the whole room now, using the air conditioning unit, you can have where you circulate cold liquid along a given arc, a given area. And that one is, I know that the liquid is being utilized. So,
okay, so most likely what I will recommend maybe for future webinars or seminars, you can also give us some of these latest developments in the market when you are doing a particular training, like what AE does, that they come up with a refresher course. So because most of the things you've mentioned here are the traditional ways of improvement in energy management, I would be interested to see if we can get the latest developments in the market, the latest technology, like that liquid cooling technology. I've heard about it, but I've not been able to come into contact with it, so I wouldn't know how it works. Yeah, thank you.
Yeah, but kujitetea kidogo, ngoja Phoenix.
Yes.
Alambe, we are in Kenya with both of you, and me, I'm in the regulator, you are in the field. In fact, I'm the person who I should recommend it to you about teaching us that. Don't assume because I work in EPLA. For me, what I was trying to do is to try to improve the energy audits in the current circumstances. And I also talked of energy auditors always updating themselves with the latest technology, me included. Like I have talked about some compressors with magnetic bearings and so on. So you can talk of that cooling racks, cooling. But I have come with a situation where you want to cool a specific position, and that's why.
Yeah, or rather to refresh my.
And that cooling act, let me finish. That cooling act similar way like a motor vehicle radiator.
So rather to refresh my recommendation, Eustace, since you people in EPRA read a lot of this energy audit and energy efficiency reports, and you come across so many new recommendations by auditors, it will be interesting to see you introduce us to new technologies. When you read through the reports and you note an energy auditor has done an excellent recommendation, a new technology, you keep track of it, and then when you have a webinar like this, you disseminate the information to the rest of us. Yeah.
That is one is okay, because in the next webinars you find people not from EPLA. I think Phoenix said we have people who are not from EPLA to teach us even as people in the regulator. And they don't peg the issue of reading to us. Who said we read a lot? We don't read a lot.
In any case, you
read a lot. And that is why we're having seminars.
But you read a lot of reports. So that's the reason.
Like I read a lot of reports without any technology.
Okay, thank you.
Yeah, you should go and read that one of liquid cooling and teach us next time. That's an assignment.
So, Godfrey, thank you very much for that point for liquid cooling. I will chime in, without specifically saying who should know that, because most of the times we've done control audits in cooling centers. We've worked with my partner. Hey, kuja. You get this air is being lost. You know, last time we did. I know Sharon is here from Mombasa Airtel. We were in her center last year, and I was showing her how she's losing air. She works there as the engineer there in the cooling center for Airtel there in Mombasa. I was telling her, Hasid actually telling her, the way we're losing a lot of air, just blowing out. We were trying actually to think how we can reconfigure the racks so that they can be cooled well. So the system Marambe is saying is good. It makes a lot of sense. But as I always say, the people who are supposed to come up with those new recommended people who interact with those systems on a day-to-day basis. Of course, also as in EPRA, when we get new things, we always also share. We share mostly maybe in this webinars, so they'll tell you.
Felix, tumepotea, sijui ama ni meeting imeisha ama ina.
No,
No,
he
it's
is
going
on. He's
on. The network is freezing.
It's a
Daktari
government
side,
network.
maybe. But Eustace, you can continue meanwhile as he
Okay. What I was
he's
saying.
back finally. Daktari, ulikuwa umepotea kidogo. You can conclude your remark. Unmute.
I was shouting to Eustace to continue talking, but he didn't hear me. I was saying most of these new things that Engineer Marambe is saying can come from any side. I don't know why you're not even looking at the lecturers here. I don't know if Dr. Wekesa is around. He's an auditor who should also be looking for new ideas and we contribute. But you see, Engineer Marambe, what you want mostly is to have these webinars controlled mostly by the auditors, not us here, because as Engineer Bukachi always says, we should not be seen like to be dictating people they're supposed to be doing. Engineering is more or less actually a uniform field anywhere. These things Eustace is teaching. If you look for Professor Luti, could teach you the same things, the late Professor Luti. So if you look for guys who work in those sectors, they can still teach you the same. So we really want to get more ideas from everywhere. We say it should be cross-pollination, where we are fertilizing ideas from different sides, then we'll pick from now like that one you've talked about, we give you that work as a consultant. You know, you consult up to outside this country, you go look for at it very nicely. Then next time when you meet, I will call you to teach on the now cooling systems, so that we can fortify the thing. Eustace, are you done with your presentation?
Yeah, to add on what
I
you have said. Or Deliver, you have something?
Just generally, in regard to what Engineer Marambe has said, I just wanted to say, in the light of learning from each other, I would also propose that most of the time I have found the EPRA, I mean, the authority sending people for control audits. And sometimes even when they are deriving their conclusion or the recommendations, maybe they need to hear from the auditor themselves on why they might have concluded what they concluded. Because sometimes I have found, maybe about 3 years ago, I used to find myself having to explain things, and already the owner of the company has been told that I have to repeat an audit. So would that be asking for too much if we say that if you have sent me to communicate to a facility that they have a control audit, then you also tell me to avail myself, because you may be having several questions when we are doing the tour, and maybe it can make you understand easily. Even as I propose a new technology, you'll be there practically to understand it. Because we have found, like, sometimes why we say that we expect what you say is by authority is because sometimes when you write that letter, you are not expecting that you would get any information from us. We have to listen to you. So if you are expecting to learn from us, you also have to be ready to be taking some of the explanations instead of writing it. Thank you.
I think that one is in order, Deliver. We don't dictate. And I think we normally call people whenever we have problems, especially with audits, even before we communicate. Like personally, I normally call people to tell them the issue. But what you have said, it's very good. And remember, we are not experts. All of us are not experts of everything. We need to learn with each other. And the reason why we normally hold these webinars is also, as I've said, we are even inviting people from outside. The other thing is the authority doesn't have infinite resources of holding these webinars. It's good for auditors to come up and with seminars for themselves, with workshops, so that they can understand from each other on those things, of which even us would be very good to understand. And the other one is, I want to disagree with Malambe saying we are teaching the traditional way of doing things. The reason why we taught it today, I would like anybody to challenge me who has ever done a cooling system in the procedure we have given. We do these things. We do these things after getting frustrated from the audits we get.
So
Yeah,
Mr.
actually,
has a question.
What I wanted to a quick one.
Just a bit,
For example, okay.
There is a question from Omari. I think Omari has to talk first. Jeremy, then we can allow Dereva to come in again.
Okay, thank you, Daktari. I think it would have been really hard on me if I did not speak today. So my question is, are there any minimum compliance standards for water chiller systems from MIPRA?
Currently, unless you explain what you mean by minimum operating standards from a chiller system, but
compliance.
Actually,
compliance
Jeremy,
standards. Yeah.
we don't have maps for chillers, eh? We don't have maps for chillers. I know some countries think of that, but we don't have it for now. Yes.
And from my experience, it's a bit difficult to dictate the minimum operation standards for a chiller, because I said you need to check the environment at which the chiller is operating. And that is why I said when an engineer installs a chiller in a given place in Nairobi, in Mombasa, during his commissioning note, he's supposed to take to establish the operating point. And we expect it to be operating at that point. Whatever we have is what we call the general engineering requirements of any operating system. It should not be operating like below a certain operating capacity, but specific, not even in April. I have not seen them anywhere all over the world. Because you see, a chiller is a complicated thing. At one point, it is operating a data center. It's operating a hospital. It's operating a disco theater. Those operating conditions are not the same. Even if you install two chillers, similar chillers to operate in those conditions, don't expect them to have the same requirements. That's why I said you need to understand the operations of a facility.
Okay, Dereva.
Okay, thank you. That's
I just wanted to the point of why I thought the point was valid to include the auditors, because sometimes, auditing sometimes is sampling, even in accounts auditing. And instead of doing sampling in a plant, what we do is we go and look at the energy consumption. We look at these are the components that consume more power. And then you do a Pareto principle, then out of like 20, you will pick about 5 to speak about. But sometimes during the control audit, someone may go and pick lights, which was far below the Pareto list. And that is why sometimes you will be told you didn't look into this, you didn't look into that, but you had a reason to do that. But because you are not consulted, that is why basically I was saying it would be good to agree and as we move together. Thank you.
I'll respond. I'll respond to that. You know, when you say when you are doing control audits, we need to call you. You will also say when we review your report on my desk here, I have 20 reports. I call 20 auditors to sit here, so that I talk to them. They need to explain to me. No, when you write your report, it has to be distinctly clear. You give your assumptions. You say what you left out. Why did you leave it out? I picked these, and you see all that kind of stuff. So when you say, I'm going to Mombasa, I ask you, will you be available? They say, no, I'm not available. So you postpone the quality control audit. So we need to try to improve. Yes, improve with time. Yes.
Yeah. If I let you continue with that conclusion, it would be unfair, because I'm not saying where every time you do, you are trying to look at a report. I'm simply saying you people call us and tell us, would you inform your client that we will be going on this day? And you might only be attending one client during the week in Mombasa, and I can basically avail myself or not. It is to my interest to avail myself. But if I am not available, you don't have to postpone. I mean, it is my problem. So I'm only saying that give us that chance.
Actually, yes, that's okay. So next time we send you a letter to send to the facility, you can come. We cannot chase you, by the way. There are times I think I've been with you to a facility in Mombasa or somewhere when you're doing control audits.
Yes,
so that can still work. That's okay, yes.
But to be honest, Most
Yeah,
of the
yeah.
times, to be honest, most of the times we are going to facilities, we go
Yeah.
through the auditor.
Oh, yeah, of course. That is what I'm saying.
We go through the auditor most of the times. We go through the facilities, but we are going to improve on that. I think whenever we are fair, we don't even reject people's suggestion before we even ask them.
No, of course, I'm saying I'm talking about 3 years ago. Nowadays, I have no problem.
3 years
I
ago,
want
sasa wewe
that-
unaleta mambo ya 3 years ago hapa saa ngapi?
Now, I
it's
think,
what-
Eustace,
yeah.
this meeting was being
Sawa
controlled by
sawa,
one
dereva, let's continue with other people.
Eustace.
Eh?
The meeting was being controlled by one Ignatius Chichi. I don't know why he went to. He saw the river and then he went under. Probably fears him. But we.
Dereva wacha kuleta mambo ya 3
Still
years.
take over the meeting. We finish.
It is actually difficult to moderate your seniors. Actually, that's what I've discovered. But Eustace, maybe we can summarize. We can wrap it up because the time is not on our side, and people are saying they'll have to pay extra for their personal drivers in the chat here.
Like in the river.
So we can summarize.
Yeah,
Sure.
if there is any other question, please ask before we call on you to conclude. That's what I was asking, because on this issue. But all in all, the reason why we hold these webinars is to ensure that the audit we get at the current conditions are at least we don't say we are perfect, because even as we are learning. The other point is, as I've always said, auditors try to invest more on trying to run more. We cannot run everything. I cannot learn how to regulate, how to do this, and new technologies. You see, I'm not a library of all those things, but it's good for even us to organize ourselves as auditors, and we chip in some little money and even get people to talk to us on the current affairs of energy audits. All in all, I'm impressed by the performance and the turnout and the questions, and let's try to improve. I think I can attest the reason why we are very passionate about this, because for the last few webinars we have done, we have seen a lot of improvement. A lot, I mean a lot, more than 70% improvement in the energy audits, which we have been getting, and we would like to even see them better. Thank you very much. And if there are no questions, you are allowed to do compliments, and we can enjoy the cool air.
Thank you. Very nice presentation. All right.
Thank you, Eustace, for your presentation. So we will share the presentation through your personal emails, and in case we don't have your email, you can always reach out to our email addresses, and I'll also share mine in the comments here. The recordings was done, and it will also be shared in our public platforms, the social media platforms. So in case you have any question, anything, you can always channel it also to my email. We will try as much as possible to address the questions. So maybe back to you, Professor, you can close the meeting.
Thank you, Chirchir, and thank you very much, our energy experts, for joining this webinar. We were 65, we are 50, and you've taken 3 hours. That's a very good, 2.5 hours, actually. That's a very good turnout. Sometimes you hold a meeting and people come after 30 minutes, they are bored. And given that it's only one person who's been talking all through, that attests to my early assertion that we are having a very good, well-seasoned trainer who can keep you glued to your screen for that long. So we are very grateful for that. As it has been said by Eustace, audits have really improved. I'm always very tough on him, telling him, reject this one. No, this one has improved. Let's give him some time to improve. And Eustace calls many auditors here and he talks to them. He's so passionate. Even if you fail the interview, for those who want to become auditors, he will call you. I've seen him talking to many auditors who have failed interviews. And I always tell him, you are the only government official who calls someone who's failed an interview and talk to him and tell him why he has failed so that he can repeat. He has done that before. So next week, we'll have another webinar. We are having our own industry guys. One has been living in smoke in boilers there in tea factory for very, very many years. So he understands the boilers from the back of his hand. Another has been working with water all through his life, pumping systems. So those are the ones who will give us a presentation next time. I really request you also come in numbers like you come today, then we will also learn from them. Otherwise, thank you very much. I would wish to close this meeting. I'm not inviting another comment from Dereva, and just wish you all the best. Check on the in the chat. There's the email for Ignatius Chirchir. He will share with you. Just write to him. He'll share with you that presentation. Otherwise, you're free to leave, unless you want to remain around and listen to Dereva.
Thank you, Prof, and bye-bye.
Bye-bye.
Huh?